Thank you so much. Okay, that was fantastic, very interesting. I already was noting down plenty of questions for the panel, and I'll just have to bug the others with them later because I've got to leave the questions for our audience. I'm going to quickly introduce Manuela Geis now, and she is going to be talking to us about explainability of AI predictions based on psychological profiling. And if you think that's a mouthful, you wait till you hear her credentials. So she has degrees in mathematics and biology from the University of Vienna and a PhD in bioinformatics and computational biology from the University of Leipzig. So you were busy. She has worked on developing mathematical models and algorithms for evolutionary biology. And currently she works as a researcher and senior data scientist at SEC Hagenberg. Her focus is on deep learning and explainable AI in application-oriented research projects. So please, the stage is yours. And the clicker.
Yeah, thanks a lot, Catherine, for the nice introduction and for giving me the opportunity to talk a little bit about our research today. There it is. So before going a little bit more into detail about our research, let me just give you a very short introduction about explainable AI. So as we can see, and we already saw it in the last talk, machine learning is becoming more and more important. It influences many parts of our life. It's not only about industry, but also about our private life. And so this raises really the need to know more about machine learning models and how they work. So the typical situation that we have in AI is the one we see here. We are given some data, we train the model, and then we get some prediction. But afterwards, very often the model is so complex that we don't know how the model gets to the prediction. When can I trust the model? Under which conditions can I trust it? Maybe if there are errors, how can I correct them? And this is exactly what Explainable AI is basically tackling, and it does so by adding some methods on top, but sometimes also integrating the methods into the AI models. I brought you now 3 examples to show a little bit where you can apply explainable AI and how it can help us. The first one comes from the medical area. So healthcare is a very hot topic in AI at the moment because AI models shall in the future assist doctors for diagnosis. And of course, this is a very sensible topic where trust for AI predictions is needed both by patients but also by doctors. And if we have explainable AI, we get some explanations for the AI model and for the predictions. This can help patients but also doctors to evaluate the quality of the AI predictions. So here are 2 examples. In the top one, you can see an AI model which is giving some factors like headache or weight, and it shall give a diagnosis based on that. And here the explainable AI comes in highlighting what features are important for the diagnosis. Or here in the bottom, the AI shall classify if there is cancer or not, just based on images. And here explainable AI can help by highlighting the parts of the image that were important for the prediction. And it does, so I don't know if you can see it, there are some little green arrows where it's pointing at the important parts. So the first one was about understanding and trust. There's another aspect about explainable AI, which is the one of learning. So in this example, an AI shall decide if a loan application gets rejected or accepted. In this case, it was rejected. But explainable AI can now tell you what features were the important ones for the rejection and where they're too low, too high. So for the future, the person can learn from that and maybe improve a little bit. And the last example comes from image classification. That's a very important field of deep learning, which is very often used. And here in this example, the AI shall distinguish between husky and wolf. And if you look at this, you would say, wow, this is a very good model. We have only one mistake here where husky is predicted to be a wolf. But if we look a little bit closer and we look at what parts of the image are actually important for the AI to come to its prediction, we see that, well, whenever we have snow in the background, I just say, well, it's a wolf. So this AI model is actually not learning the animals, but it's actually a snow detector. It learns there's snow or there's not. So in this case, the explainable AI helps us to detect some weaknesses of our model. In this case, it's on the level of bias in the data. So that's my first slide of the introduction. This is just a quick overview about the current status that we have about machine learning models without explainable AI and about interpretability. This is very simplified. It's not always like that, but especially in situations where we have complex data, complex problems, it's a good approximation. And what we have is we see a trade-off between the explainability and the performance of models. So decision trees, linear regressions, for example, these are very, very easy models or simple models. They're not complex, but in many situations where you have complex problems, they perform not that good, but they're interpretable. So for such applications where you need more complexity, you would go for more complex models like deep learning models, but you lose your interpretability because they're, well, even for experts, hard to interpret. And this is what Explainable AI is working at, to tackle this trade-off that you see here. At SCCH, we are currently developing a new Explainable AI approach. It's called BAPC, which stands for Before and After Parameter Correction. This is a research project I'm working with together with Florian Sowiecki and Maima Samut. Our model or our approach falls into the class of the so-called model agnostic approaches. So in Explainable AI, we basically have two classes of models. There's the one of model-specific approaches, where you have an Explainable AI method which is specifically designed for one type of AI model. So this cannot basically not be applied to other models because it uses the model architecture, also learned parameters. And there is the group of model agnostic approaches, which is basically independent of the AI model itself. So the AI model can really be a black box. I can interchange models so that I can compare different models. This makes the approach very flexible and universal. And our approach is such an approach. Our approach is, however, designed for a very specific use case, or not very specific. In industry, you very often find this. You very often have some data which you approximate by some more simple machine learning model. Might be a linear regression, or maybe you have some physical formula where you fit the parameters, but it's so simple that there is still some error left. And what you then very often do, you apply a more complex model for correcting the error, for example, a deep neural network or random forest. But the problem is that this one, the error correction model, you cannot interpret because it's too complex. We aim at interpreting also the error correction. So the base model is already interpretable. We also want to interpret the error correction so that in total we can interpret everything. You can think of this situation as a student writing an essay, it gets some correction from the teacher, but without the explanation of the teacher, he cannot understand his mistakes and he cannot learn from it for the future. So this is our approach. I quickly walk you through it. What we do, we want to make the error correction AI model interpretable. And we do so by using the base model, which is interpretable. So what we do, it's a three-step process, basically. So we have a system that we want to describe, but that we want to predict. We have some data, X and Y, that's our training data. In the first step, we apply the base model. We train the base model, might be a linear regression, physical formula, whatever, must be interpretable. Then in the second model, we train the AI model for the error correction. So, and the first and the second step together, they give us our improved prediction. And then we have a third step, which is only for the interpretation of the AI correction model. And what we do here is we fit the base model again, but on a little bit corrected input data. So what we do, the first fit of the base model was on X and Y. The second fit is on X and a corrected Y. The Y is now corrected by the error correction from the AI model. So we subtract Y minus epsilon, but the predicted epsilon from the AI model. So, and then we compare the two base models. Basically, we're looking at the difference in the parameters. So here's theta and theta star. And this we interpret as the effect that the AI model has. I give you a very simple example. Here's some simulation that we did. So in plaque, so what we have here, we have the velocity of a falling object in time. We want to predict the velocity. The black dots here, these are the training data. The base model that we fit in the first step is just a linear regression, so very simple. That's the blue line in between, in the middle. Then we apply an AI correction and the improved prediction, so base model plus AI, is just the light blue dots here. And then in the third step, we apply the base model again, this time on corrected data. But what we do here, I didn't mention that on the last slide, we only correct the data within an interval. In this case, we choose this interval 2 to 3. Here we correct our input data, we fit the base model again. We now get the orange line here, and what we see is, compared to the blue line, the orange line goes more down, so it follows the trend of the AI model. It's closer to the AI model. So apparently it mimics the effect. And in the end, you would just then compare the parameters. So, but now we come to our research project. What we do is we work together with our industry partner, Speed Invest Heroes, and we want to predict the success of startups. We want to do that in an interpretable way, and we want to use psychometric data. Why psychometric data? Well, studies showed that one of the top reasons that startups fail is actually that they don't have the right team. So you need the right mix of people to have a successful startup. And Speed Invest Heroes does some studies based on some questionnaires that they're doing with founders and startups. And they found out that actually some personality traits are different for founders and non-founders. For example, the activity level here, and you see some others. This is our motivation. Since we didn't have much data in the beginning, we started with a pre-study to develop our method, and I want to present this to you here. So we artificially created some toy data, and we did so by using the news vendor model, which is a mathematical model and is very popular in applied economics, for example. The story here is that there's a news vendor boy who buys newspapers in the morning and then sells them during the day. And the question is, well, in the morning he doesn't know about the demand during the day, so how many newspapers shall he buy in the morning without knowing the demand to maximize his profit? And this is modeled by the news vendor model. Of course, we are not interested in newspapers. We think of it as a company that produces some product and sells it and doesn't know the demand beforehand. So let's focus here on the images. Don't look at the text. So we created our data set. It's a data set of 100 data points. The first half, so the first 50 data points, are the black dots. You can see we just generated them according to the news vendor model, and the second half of the data set, the blue dots, they're generated a little bit differently according to the news vendor model, but then plus some more products that they produce. So they're a little bit, they have more risk affinity. They're a little bit more risky, which you can also see in the plot here below. So when there's a very high demand, the strategy pays off, so they get more profit, but actually on average, the profit is lower than the one of the black dots. So this is our training data. This we will use to for BAPC to predict the success of a company. And success, we just mean, okay, profit is positive. Keep it simple. I don't want to show you here all the details, just a few words. So what we did, again, we applied the base model first. This is the blue and the black dots you can see here. Then we applied the AI correction on top. This is now the red dots. And without going more into details, we figured out, okay, what's happening here is that with the correction, the black dots move to the right, or at least some of them, and some of the blue dots move to the left. Then we apply the base model a second time, now on the corrected input data, and we see that again, black dots move to the right compared to the left image, and the blue dots move to the left. So again, we see that the second fit of the base model can mimic the AI correction. That's very good. That's what we want with BAPC. And the last step is we need to look at the parameters from the first base model and the second base model. And the difference again is the interpretation of the effect that the AI model has. In our case, we just only have one parameter, it was lambda. It's just the inverse to the average demand. We looked at it, you can see it here in the picture, for 2 different AI models for random forest neural networks. We found basically that on average, in the second base model, so after AI correction, the parameter was smaller, so the effective demand in the first base model was underestimated. That was an average, but you can also look at it for single data points. And for single data points, you know about the risk affinity, if it is there or not. And you can look at the lambda, if it was smaller or not. And like this, you can link the psychological factor risk affinity to the econometric factor, which is in this case demand. So we only have the demand here in the model. But we have this psychometric factor, which is not in the model, at least not in the distribution, but we can still link it with the approach. And this is a concept that we want to use in our research project that we want to apply here. So as I said, together with Speed Invest Heroes, we want to predict the success of startups. We want to do it by using psychometric factors on one hand and econometric data on the other. So econometric data is like valuation, for example, or head count of a company. Psychometric factors, we have like about 50 or so. Some of them you can see here. And what we do as a base model, we want to use decision trees that can look like this one. They're very nice and handy because they are easily interpretable even by non-experts, which makes them very nicely. They can look like this one here, but that's only an example. So here at the inner nodes, you see the psychometric data, for example. That's one variant we are looking at. But we are also looking at another variant where we have in the base model only the econometric data, and in the AI model we have only the psychometric data. And then again, we would have the interpretation of the psychometric data in terms of the econometric data, which is very nice because the econometric data are in general easier to measure than just psychometric data. But that's just a teaser because we are still in the process of developing everything and results are not ready yet. So yeah, this is a teaser for our true work. Yeah, this already brings me to an end. I hope that I could convince you somehow that explainable AI is important for understanding AI models. I presented you our new approach, BAPC, that we currently develop at SCCH. As I said, it's about, we have an error correction AI model that we want to interpret, and we do it in terms of the base model by comparing parameters before and after the correction. And we want to apply this in our research project for the prediction of startups using these psychometric factors, which I show you are also important. Yes, and the very last point is we want to interpret the effect of the psychometric factors in terms of the econometric factors. So as I showed you, psychometric factors probably in the AI model, econometric in the base model. And with this, thanks a lot, and I'm open for questions, of course. Or maybe later, I don't know.